All this motive power can be put to best use through the suspension system. It's something of a miracle to launch a 7,000-pound behemoth into the air high enough to jump over itself and then some, and have it land perfectly graceful as a cat. If our normal SUV leaves the ground at all, handling will be severely compromised when it touches back down. It may experience repeated bounces, as body roll and direction of travel are affected in unpredictable ways. The race truck seems to handle everything with great skill, both small bumps and huge jumps alike. Let's go right to the heart of the suspension, the spring and shock absorber. And then we'll zoom out to connected parts and see how the system can take in such a wide range of obstacles. Springs are the main component tasked with holding all the vehicle's weight and absorbing bumps. Shock absorbers aren't meant primarily to hold weight, but rather to tame or damp the motion of the spring. Our truck has a dual spring setup that comes with a number of desirable benefits. First, for the extreme suspension travel distance, a single very long spring at this length might have issues binding or bending in undesirable ways from full extension to full compression. The two springs are attached to a sliding retainer in the middle that keeps everything aligned throughout. The smaller top spring is also softer. Under normal cruise, they work together for a softer, smoother ride. However, as the system compresses, the sliding ring butts up against the stop collar, which removes the top spring entirely, leaving the much firmer, heavier bottom spring to handle things from that point on. This is what's called progressive spring rate, where one system can handle both soft and firm requirements. Without progressive springs, the ride might be too firm when cruising for poor, jittery handling over high-speed, flatter sections, or far too soft to land a jump or navigate big obstacles without breaking things. Even this highly tuned spring system would experience chaotic bounciness on its own. Nearby shock absorbers are specially built and tuned to eliminate extra spring bounces as much as possible. The body of the shock is filled with oil. Inside, there's a moving rod with a piston at its end, and holes or ports that allow shock oil to pass through. Some ports flare open towards the top to affect flow during the compression stage. While others open towards the bottom for the rebound stroke. There are stacks of thin, flexible washers, top and bottom, that can be swapped out to alter how fast oil can flow through these ports. And allow separate tuning for compression versus rebound. An attached reservoir with a relatively stationary piston and nitrogen charge keeps the oil portion properly pressurized during all this movement. Like the spring setup, it's desirable to have softer or stiffer zones as the shock travels its range. To make some parts softer or stiffer, there are bypass tubes in the shock wall that lets some oil bypass or flow around the piston entirely. There's an adjustable valve at one end to allow or restrict the flow for a softer or stiffer piston feel. This special valve is also one-way, and it's designed to close if the piston goes the opposite direction. Meaning this particular bypass can only affect shock compression. The tube has a preset length and can only work while the piston is in its range. By using various bypass tubes, you can tune different parts of the shock for more or less oil flow, and softer or stiffer shock feel in that zone. These three tubes have one-way valves for compression. There are two additional bypass tubes at the other side for the rebound stroke. The high-tech shock absorbers have a ton of adjustability to skillfully handle a wide range of conditions. All this movement generates a lot of heat, so there are nearby reservoirs with fins mounted higher up in the outside airstream, which allow hot shock oil to circulate through for cooling. Shocks and springs are mounted to reinforced frame supports at the top, and an engineered swinging beam called the trailing arm at the bottom. To complete the assembly, there are smaller bump stops above the axle that compress at the absolute limit of travel. In my research, I noticed that these bump stops come into use way more than I thought they would. They're driving these trucks at the absolute limit all the time. Trailing arms attach lower on the rear axle, with separate rods at the top, to allow for a lot of travel while keeping components properly aligned through the full range, especially axle joints. This is called a 4-link suspension. The long trailing arms are also a key design component in making these trucks seem to float in a straight, level path, no matter the chaos unfolding at each wheel. If you draw a line from the tire contact patch to the trailing arm pivot point, this line represents the direction of all the drive force coming from the rear end. As long as this line is in front of the vehicle's center of gravity, the wheels will tend to pull the vehicle forward in the direction of this line. Our classic 4x4 shows how this looks with a more standard rear axle setup, where the driving force remains behind the center of gravity and tends to pull things upward for a bouncy ride. Keeping that center of gravity behind the line of force is why you'll often see lots of weight hanging off the back of desert race vehicles. Things like spare tires, tools, and so on. Continuing with the trailing arm, we see the attached sway bar near the axle. It connects both trailing arms and the truck's frame together with a rigid but flexible bar that twists with suspension travel at each side. This limits excess body roll in corners and keeps both tires in contact with the ground as much as possible.